We're going to talk about thermal expansion. First of all, I'm going to explain what is behind thermal expansion at the molecular level. I'm going to get straight into that. Well, let's imagine that we have some particles at a low temperature, and then you add some heat to it. What's going to happen? Those particles get energy. They use that energy to get kinetic energy, to make it go into motion, make them go into motion, so they start to move all around. And you know what's going to happen? At the macroscopic level, at the bigger level, not at the microscopic level, but at the bigger level, when you can see over here from the outside, well, it's going to take up more space. The substance is going to be looking, it's going to become bigger. That's what happens when you add heat to an object. It expands. That's pretty much it. That's the idea of thermal expansion. And also, when you lower the temperature of a substance, the molecules have less energy, so they stick to each other more than before when you had the bigger temperature. Now let's see an example. For example, let's say we have this water, this container, this beaker of water filled with water, and it has a regular temperature of 70 degrees, and then you increase the temperature. You know what's going to happen with the water? Well, that this beaker has the same amount of water. I mean, I did not change it. Did not change it at all. Didn't put more water. What you see here, it's that the volume increased. It's the same mass, but the volume increased with the heat. So it becomes bigger. And what happens over here after 180 degrees? Well, this water is going to be spilling out from the container. All of this water comes out because it can't stay in this container. All right, that's what happens, guys, when you increase the temperature. The volume increases. And it's not just going to happen with the water. It also happens with other substances, such as this one, such as concrete. This, maybe you've seen it before. This example, it's, for example, here, two pieces of a road. And due to the heat, they came together and they cracked. So that's a problem when you make roads and also boardwalks. For example, this one, due to thermal expansion, the blocks got bigger. The person who made this uh, boardwalk, this sidewalk, was maybe they put the tiles too close to each other, and when they expanded, the blocks cracked. That's a problem. So that's why when we make sidewalks and roads and whatever, there has to be a division between each big section so that they can expand. And also, they have made roads with these type of devices in order for the roads to expand. Maybe you've seen them in some places. The reason for these things on the roads, it's so that thermal expansion of the concrete will not destroy the rest, will not destroy the road, because thermal expansion is there. And we can also see these effects on other types of roads, for example, on train tracks. Maybe this would happen back in the past when we didn't really know how to build the train tracks. For example, here when they expanded, they got together too much and they started to curve. You had these effects. Of course, we've come a long way since our beginnings in train track engineering, and we have found that the solution is to give it a gap between the two rails. Between the rails, you gotta put an empty space in order for them to expand when you have the summer temperatures that are very high, such as here. For example, here we can see another gap. This gap is going to be like this when it's in winter, but in the summertime, those two tracks are going to be coming very close to each other. And if there would be a very high temperature, well, too bad, because probably the rail tracks are made, this gap, it's just going to be working for a certain temperature. But if we have some global warming, it's going to be a problem for this train track because it's designed for a given amount of temperature for the summer in that part of the world. And where else do you see thermal expansion? Well, you know what? In your mouth. For example, if you ever had that bad experience of getting cavities, you know, a cavity, it's a bad thing. It's when you got some tooth decay. You go to your dentist and he's going to be removing that cavity. He takes it away, he starts uh, picking on it, and he removes, or she removes, the cavity, takes away all that bad stuff. There's going to be an empty space. That empty space has to be filled with something. It's gonna be empty now. What do you do? What does the dentist do? Well, he's gonna put there a resin, an amalgam, or maybe gold or whatever. And once it's there, well, you're happy to go. But the dentist doesn't just place anything in there. It has to have certain characteristics. It has to be very close to the properties of your tooth, and not just in its appearance or other obvious properties, but also in its thermal expansion. Because imagine that the doctor placed your tooth filling at 37 degrees Celsius. That's why do we have this temperature? It's pretty high, but that's your body temperature. You know what happens when the temperature gets cooler on the outside? Well, your temperature inside eventually will also get cooler. And if the thermal expansion coefficient, which is a term that we're going to be talking about a lot, is less than the thermal expansion coefficient of the teeth, or your tooth in this case, well, this thing, it's going to be, or actually, if this thing is, or if the coefficient of thermal expansion is different than the expansion coefficient of the tooth, well, it's not going to be getting bigger and smaller when the temperature changes. For example, if the thermal expansion coefficient is actually bigger than the thermal expansion coefficient of your tooth, well, this thing is going to be smaller when your temperature decreases. So the idea, guys, oh yeah, and also if we get a warmer temperature, if the temperature gets greater, well, the filling is going to be bigger than your tooth, and you can imagine that that's going to be a problem because that's going to be making your tooth expand. And then when you get back to your 37 degrees Celsius, your teeth is now bigger, and there's going to be an empty space, even though that this is back at its volume that you had when you had 37 degrees Celsius. Your tooth got expanded. So you see, it's a big problem if you don't have a thermal expansion coefficient that is exactly the same as the teeth. So that's why they use special resins and ceramics that are pretty much the same thermal expansion as your tooth. And as you can imagine, when this thing is bigger, when imagine there's something growing inside your teeth, and it's pushing all around you, that's going to be hurting your teeth, guys. It's very uncomfortable. And also imagine that this is going to be smaller. Well, it's like having the cavity back again. It's going to be hurting your tooth again. And also imagine getting gunk inside there. It's going to get dirty. It's going to make an infection, and it's going to be bad. So that's why thermal expansion is something that dentists need to know in order to make the tooth fillings, or at least the dentist technicians need to know about this. Alrighty guys, so that's the problem when you get a filling that is not the same as, it's not the same in thermal expansion as your tooth. There's going to be a gap, and gaps are okay when you have, for example, the road, but when you have your teeth, your fillings, they have to be of the same thermal expansion, so that when your teeth grows, or your teeth also grows when you have a higher temperature, the filling has to grow and get smaller and contract at the same amount as the filling and the tooth. Alrighty guys, let's continue. You can also see this problem of thermal expansion when you go to the refrigerator and you get the jar of strawberry. I mean, that strawberry jar, you closed it yourself with your own strength. But then when you go back to the refrigerator, I mean, you can open it and close it with your own strength, right? But then when you leave it at the refrigerator, after a while, after a week, you decide to go back and eat something like a hot cake, and you want to get some jelly on your hot cake. You haven't opened this container for a while, and nobody else has opened it. You try to open it and you can't. Why is this? Well, the idea, guys, it's that the thermal expansion coefficient for each material on your jelly jar is different. The jelly jar has glass and metal. And you know what? Guess what? The metal container, the metal substance has a coefficient of thermal expansion that is going to change more depending on the temperature than the glass jar. So the metal contracts and expands more when you have a difference of temperature than the glass. So when you lower the temperature, the metal container is going to become smaller. The metal cover is going to become smaller than the glass jar. And that's thermal expansion in your life, guys. That's going to be a problem. And the only solution is to take your jar and place it in hot water, but only the metal part, so that this metal part can expand again, and it's not going to be so tight. And then when you try to open it again, it's going to be easier. So that's thermal expansion in your everyday life. Now let's go to the equations. Let's imagine that we have this bar. This long bar made up of some material, doesn't matter right now. Let's say that it's some material. But I want you to notice that this thing is going to have something that is very important. If this is going to be very long, the sides, the width, and the height, they're not going to be very important. What's going to be mattering, what's going to be the most important part of this thing is going to be its length. So I'm just going to focus on the length of this bar. When you have a bar or a wire or something that is very long, that's going to be its most important characteristic when we talk about thermal expansion. Alright, so it's going to have a length, and you see here it says Li. That's going to be the initial length when you have a given temperature, and afterwards, after you increase the temperature, what's going to happen? Well, that thing is going to be growing. It's going to have an extra length, and it's going to have an extra part. It's going to be growing due to the increase of temperature. So that extra excess, that extra part, that's going to be called the delta L, the change of length, because it increased by a given amount, and we're going to call it the delta L. That's going to be that little part that you get when you increase the temperature. And the mathematical equation that represents this delta L is going to be this. Delta L equals alpha times Li times delta T. So the amount of how much it increases depends on three things. It depends, first of all, on the substance. So if this is, for example, metal, it's going to be getting bigger and smaller, depending on the change of temperature, of course, than, for example, some type of, let's say, Pyrex laboratory glass. And some materials are made so that their thermal expansion coefficient is very low. Well, some devices are going to be made with those substances so that they're not going to change a lot. And they're going to use specific coefficient of thermal expansion materials so that they're not going to change a lot. But for regular things, for example, um, for example, um, the thermal expansion coefficient of a metal, it's going to be, well, it's going to be such that it's going to be increasing a lot your length. But some other materials are not going to have such a big coefficient of thermal expansion, and they're not going to be increasing as much. So what I'm saying, guys, is that the delta L, how much it's going to grow, depends on the material. Some materials grow more than others when you use the same amount of energy. And the other thing, guys, that is very important to know in order to see how much this delta L is going to be, it's going to be the initial length. And the initial length, it's going to be, why the initial length? Because this is going to be with how much material we can work with. So if you have a small amount of Li, of initial material of the length, well, you can't grow as much as if you would have a bigger amount. So that means it depends on the initial length. If you have a small amount of material, well, you can't get more. You can't get more than what you actually have. So it depends on the material that you have. It's not going to be growing it infinitely. It depends on what you have. Okay, that's the idea of this part. Now, it also depends on the delta T. And of course, delta T means TF minus TI. What you had before, the initial temperature, and what you had afterwards, which is the final temperature. When you subtract them, it's going to be the delta T. So depending on how much the change of temperature is, you're going to get your delta L. Alrighty, that's what this means. So the change of length, it's going to depend on these three factors: what material you have, the initial length, and also how much the temperature changed. And after you get the delta L, this is going to be the increase of the length. This is the original length. The full length is going to be LF, the final length. Okay, so that's going to be the length that usually they're going to be asking for. The length of the material after you have the increase in temperature. And the final length, it's going to be given as you see graphically here. It's the Li plus the delta L. That's why you have this equation. And we know that delta L is this, so we can put together these two equations in order to get the final length depending on the coefficient of thermal expansion, and all of these things. We can put these two equations together and we get this. The final length equals the initial length plus the coefficient of thermal expansion times Li times delta T. Because delta L is this amount, and we know that the final length, it's made up of the initial length plus the increase that is dependent on these factors. So you get this equation. Now we're going to get a little bit fancy. We're going to do some factoring, some algebraic factoring, and we get the following equation. So you see we get an Li in this part and an Li on this term. We can factorize it. The Li is going to be on the outside, and what's going to be inside these parentheses? Well, it's going to be a 1, so that you can go back to this equation by multiplying. Li times 1 gives you this. And then Li times all of this is going to give you back this equation. So as you can see, this is going to be making your operations a little bit more efficient, because here you got to use Li on this term and then Li back again over here. Well, you got to use the same number on these two parts of the addition. Well, you can simplify that by just doing this. You can do first multiplying this. You can first multiply this and then add with the 1, and then add 1, and then at the end multiply by Li instead of multiplying instead of using that same number here and then here again. Alrighty, guys. Now this equation, it's going to be for when you have a long material or a long object, for example a wire or a bar. But what happens with other things that don't have this shape? For example, a plate or something that is in 3 dimensions. How do you get the volume expansion and how do you get the area expansion? It's going to be the same formula, but instead of, for example, alpha delta T, that formula is going to change in the following way. So it's going to be, instead of alpha delta T, it's going to be the double of the alpha. If you do all the algebra and you multiply the LF times the LF on this side and you do this equation for this area, you're going to get this result. And also if you get this, if you do the same procedure, if you do LF, if you measure the LF on this edge of the cube and the LF on this cube and the LF on this part, and then you multiply them all, you're going to get at the end an equation like this one. That's the origin of these equations. But they're pretty obvious, right? I mean, pretty easy to remember, because as you can see here, there's a 2 for 2 dimensions, and you got to multiply by 3 for the 3 dimensions, the same coefficient of thermal expansion. So it's pretty much the same equation for when you get something that is not a bar or a wire. For example, when you have a plate, this could be used, for example, for getting the area expansion of a mirror or a glass or anything that is like that in that shape. For example, a piece of paper. Also, it can expand when you increase the temperature. And volume expansion, well, pretty much everything has volume. We should use actually this equation for all of these cases, but since you're not going to be having so much of an effect on the width as you do on the length, and which is going to be pretty much the most important part, the length, that's what you care about a wire. Well, we focus on this equation. And also in this part, when you talk about a piece of paper, you don't really care about the how thick it is. You only care about its length and its width. So that's why we talk about this equation. But if you want to get really nitpicky about these things, you should use this equation. But no, guys, if they give you a problem where you have to calculate the length of a bar, well, you got to use this equation, and so on. And so this one is going to be for when you have the example that I gave you at the beginning, the beaker, the container filled with water. I'm going to use that for a problem in a while. So we're going to get to problems, but before we get into that, I need to give you some more information about the materials. For example, here we have aluminum. It's going to have a coefficient of thermal expansion of 23 times 10 to the power of negative 6 over degrees Celsius. That's the unit for this thermal expansion. It's 1 over degrees Celsius actually. And we have here several materials, several substances which all have their own thermal expansion. And as you can see, the water has the greatest thermal expansion. So water is going to be getting bigger or smaller depending on a change of temperature. And with that same amount of change of temperature, it's not going to change as much the diamond. So if you increase, like for example, 50 degrees Celsius, a substance that has the same temperature, for example, water and diamond, the water is going to expand more than the diamond. And as you can see here, the aluminum is going to be expanding more with that same increase of temperature than these other materials. So what I'm saying, guys, is that if you have in a room at the same temperature, aluminum, a piece of aluminum, your concrete, a diamond, maybe a ring, I don't know, a glass window, and stainless steel and water, puddle of water, and you increase the temperature, you know what's going to happen? The water is going to be increasing more than all the other substances. And then after that one, this aluminum is going to be also increasing a lot than all the other guys. And the diamond is going to be the one that stays pretty much at the same length or volume. Alrighty. So that's going to be the thermal expansion coefficients, which we will be using for the problems that I will give you. So you gotta hold on to this table. It's also found in your book. So this is gonna be the table that we will be using. These are gonna be the values that we will be using for the problems that you will be receiving. Here's one such example problem. An aluminum bar has a temperature, okay, aluminum, okay, so it's this one. It's going to be this alpha. That's the one that I'm going to use for this problem. Has a temperature of 20 degrees Celsius. That's the initial temperature. And a length of 50 meters. Doesn't say the width or the height of it. We only care about the length. And it says, what length will it have if the temperature becomes 300 degrees Celsius? Now, don't worry about that aluminum bar. It's not going to melt. Its melting point is actually about 600 degrees Celsius. So that aluminum bar is still solid aluminum. Alrighty? But it's going to be expanding. How much bigger will it be after the change of temperature? Well, we're going to use the following procedure. We have this equation, which is LF equals LI times all of this. Delta T, you should change it to TF minus TI, or you can calculate it before. You just subtract 300 minus 20, gives you this amount. And then you got to multiply by the thermal expansion coefficient, which in this case is 23 times 10 to the power of negative 6 because we have aluminum. If it would have been some other material, for example, silver, if that bar would have been silver, well, it's not here. If it would have been, for example, steel, let's say, you would use this number actually. And that's why in this case we got to use 23 times 10 to the power of negative 6. So then we got to add, we got to multiply first this thing because that's inside the parentheses. This parentheses goes from here to all the way over here. So you got to do first this multiplication and then you add it with the 1. And then we get this amount. This amount times 50 gives us finally our result. So as you can see here, even though we increased the temperature by 280 degrees, there wasn't such a big change. It's not like thermal expansion is going to give us like, oh, if I increase the volume, it's going to give us like the double of the length. No, 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 it's not going to be that much. Because as you can see here, the thermal expansion, it's a very small number. 23 times 10 to the power of -6. That's 0.000. Well, it's going to be 4 zeros, 0.00023. And that's a very small number. So that's why the thermal expansion effect on your length, it's not going to be that much, even though you increase the temperature by a lot. So that's why it just changed from 50 meters to 50.32 meters. That means that it increased by 32 centimeters. Well, that is kind of, I mean, if you have 50 meters, that's a lot. It's pretty long. And those 32 centimeters, you're not going to notice so much unless you're looking into it very closely. Anyways, that's what I'm saying here. It increased by 32 centimeters. So we got a problem, and we know the final length, which is 50.32. So that was the question. What length will it have? Not how much it increased. If they ask you for how much it increased, all you have to do is just do this. Alpha times delta t times Li. But they asked for the final length. So you got to add it with the initial length. And that's what you have here. That's 50.322 meters. Alrighty. Now I'm going to show you the equations for when you need to get the initial length and all the other ones. So I'm going to give you the algebraic clearings, or how you solve for the other variables. For example, here we have the equation that I gave you before, and let's say that we want to know the initial length. What do? Well, it's pretty basic. This thing is all of this parentheses. It's like a factor that multiplies the Li. It's multiplying it, so you got to divide everything by this amount. That's why the equation for Li is going to be the LF divided by the sum of these guys. Got to put parentheses when you do the operation. And that's Li. Now what if I want to do alpha? Well, this equation, I got to change it to this form in order to get a better way to clear for alpha. And as you can see, alpha is the thermal coefficient of thermal expansion, right? So what I have to do first is this Li, it's being added, I gotta subtract it. So that's why we have LF minus Li. And then this Li times delta t is still there multiplying the alpha. I gotta pass it as a division. So it's LF minus Li divided by this. That's gonna be your thermal coefficient expansion term, right? Alrighty, guys. And this is going to be used, for example, if they ask for the thermal coefficient expansion. The coefficient of thermal expansion, guys. When they ask you for that, you gotta use that equation. Alrighty. Now, what if you want to get the final temperature? What do? Well, you should use this equation. And what do we do with it? It's gonna be this. Pretty much the same as before. This Li is being added. You gotta subtract from both sides, and you get LF minus Li. And then after this, you can see that we want TF. So this alpha and this Li, I don't want them there. So I gotta divide everything by alpha and Li. So it's gonna give us something like this. And as you can see here, we want the TF. I don't want TI. It's being subtracted, so I gotta add in both parts the TI. So we get this. So you gotta do first all of this, LF minus Li, and then divide by this product, and then subtract, and then add it to the initial temperature. And that's gonna give us the TF. So this thing, this part of the equation represents the change of the temperature. So if they ever ask you for the change of the temperature, this is it. This is the equation. This little part, LF minus Li over alpha times Li, that's what you're looking for to get the change of the temperature. That's delta T. This part is delta T. So delta T plus Ti will give us Tf. And then here's the final equation that I'm going to give you. What if I want to know the Ti? For getting Ti, all you have to do is, you see this thing is being added? Now we got to pass it as a subtraction. So it's going to give us this equation. So Ti equals Tf minus all of this. That will be your equation for when you want to get the initial temperature. Here's another problem. Here's a problem that uses area. Let's say that we have a glass hole and we got a glass. Okay, this is a glass, right? This is a plate of glass. And we cut a circle that is going to be a hole. So we got a circle. We have a hole in the shape of a circle. And they tell us that the diameter of this hole is going to be 90 centimeters. The question is, what's going to be the area of this hole after you increase the temperature by 200 degrees Celsius? It says it increases the temperature, so that's going to be the delta T. When they just tell you it's going to be increasing by, or it increases, that's delta T. It's not TF, it's not TI, it's delta T. They already told you the change of the temperature. So we're not going to be worrying about the TF and the TI. They gave us already the delta T. And they're also going to be asking you for the diameter. What's the diameter of that hole? Because the glass is going to be changing, not just the edges, the straight edges on the glass, but also this circle part. It's going to be increasing. It's going to be changing. Everything, this whole piece of glass is going to be changing. So what's going to be the new diameter after you change the temperature by that much? We're going to do the following. Of course, the formula for the area does not take the radius. Doesn't take the diameter. It takes the radius. You got to change that diameter to radius. So the diameter is 90 centimeters. 90 centimeters is going to be 45 centimeters. You got to divide it by 2. That's why we got 45. Those are centimeters. Those centimeters, you got to change them to meters. So 45 centimeters, it's going to be 0.45 meters. That's going to be our radius. Now we're ready to change that to area. So you do pi times radius squared. So the radius is going to be 0.45. You got to square it, then multiply by pi, and we get this amount in square meters. The delta T is 200 degrees Celsius. So that's the change of temperature. We can use this equation. And I placed the AI at the end, but it's the same as the previous equations. Alrighty, guys. So what's going to happen here? And what's going to happen here? Well, we got 1 plus the double of alpha. It's the same formula as before, but we got to double the alpha because we're talking about an area. That coefficient of thermal expansion has to be multiplied by 2. And it was glass. We got to consult our table that I gave you a while ago. Glass is right there. It says 9 times 10 to the power of negative 6. So there it is, 9 times 10 to the power of negative 6. That's going to be the alpha. Delta T is 200 degrees Celsius. We got to do all of this operation. We multiply at the end by the area, the initial area, which is the area of the circle. That's what we're concerned about. And that's going to be the area of the circle after you change the temperature. It's going to be 0.6383. It used to be 0.6361. So it increased by that amount, which is like cubic millimeters. Anyways, or something like that. It's a very small amount. It increased by very little. But the question was also, what is its diameter. So this area that I got here, I gotta change it to radius. And to do that, I gotta clear my area formula for the radius. And it's gonna be this pi is multiplying, so you gotta pass it dividing, and that square, it's next to the r. You gotta pass it as a square root. So you get this new equation. And the radius, as you can see here, it's gonna be 0.45075. As you can see, it just increased by a very small amount in millimeters. It used to be 0.45, now it's 0.45075. It increased by very little, as you can see now. And the diameter used to be 90 centimeters. Well, now it's going to be 90 centimeters plus 1.5 millimeters, a very small amount. So it had just increased by about 1.5 millimeters, the diameter. That's the new diameter. It's going to be 90.15 centimeters or 0.9015 meters. And that's it for this problem. Let's continue with the next one that I find pretty interesting. Let's say we have a beaker. A beaker is just a container that you use in the laboratory. It's just a glass that you place things inside of it. I mean, it's just a container. And this container is going to have, or this beaker is going to have, a volume of 0.1 cubic meters. Okay, can you imagine it? It has that volume, 0.1 cubic meters. And then it says that it's filled with water completely. So to the brink, it's going to be filled with water. What's going to be the volume of this beaker? Well, the volume is going to be pretty much the same as the volume of the beaker. Let's imagine that this glass is very thin, so it's not going to be changing that much. But if we would have to be more precise, then you would have to take into account the volume of the thickness of the glass. But let's imagine that both bodies, both objects, the water and the glass beaker, the container of the beaker, it's going to have the same volume. So the volume of the beaker is 0.1 and the volume of the water is also going to be 0.1 because the water is filling the whole container. And then it says after the temperature increases to 100 degrees Celsius, how much water will be spilled? So let's imagine that the water is at 0 degrees Celsius and it changed to 100 degrees Celsius, which is before it changes into vapor, so it's still water, and it started from 0 and it ended at 100 degrees Celsius, so it's still liquid water. Question is, how much water will be spilled? Because as I said before, water has a coefficient of thermal expansion that is very big, so it's going to be increasing. It's going to be getting bigger. It's going to be expanding, thermal expansion. It's going to be getting bigger. So it's going to be getting out of the beaker. It's going to be spilling out. But wait a moment. Wait one moment. That glass, it's also being subjected to the same heat. That temperature is also going to be increasing on the glass. So let's imagine that both of the objects are increasing by the same amount. So they're going to be increasing by the same amount of temperature, but of course we know, guys, that when you add heat to a substance, it depends on the heat capacity, right? So we're gonna imagine that both of them are going to be changing its temperature by the same amount. Let's imagine that both of them change their temperature by the same amount, and what's gonna happen with the beaker? The beaker, guys, also expands. Not just the water expands, but also the beaker expands. The beaker expands, so we're going to have a new volume, so it's not going to spill as much as if it didn't expand it. So it's going to be made up of regular glass. In the laboratory, they actually use beakers of Pyrex, which is a special type of glass, which has a very low thermal expansion coefficient, and it's not going to change as much with those changes of temperature. But let's imagine that this beaker, it's made up of regular glass. So let's see what happens. Alrighty, guys. So we have the following. The volume of the water and the volume of the beaker are not going to be the same. The volume of the water is going to be this much. So it's going to be 3 times the alpha, which in this case, the alpha is this amount, then times the delta T, which is 100, and then we got to multiply by the initial volume, which was 0.1. We make this multiplication and we get this new volume. So the water is going to be changing by this much. It used to be 0.1, but the water is now going to be 0.10207 cubic meters. And the volume of the beaker, as you can see, it has a lower thermal coefficient of expansion. It's now going to be 9 for the glass. We make this operation and we get this amount, which is not as big as this one. And as you can see here, this is now going to be the volume of the container. This is going to be the maximum amount of water that it can receive. This is the water that you have now. So how much water is going to be spilled? Well, to get that, the spilled volume of water is going to be the volume of the liquid minus the volume of the container, because the volume of the container is going to be the volume of the water that's going to stay inside of the container. But the full volume of the liquid, it's going to be both outside and in the inside. That's why we got to subtract the full volume of the liquid minus the volume of the container to know what's going to be on the outside, what's going to be spilling out. So we got to subtract these two new amounts and we get this. So this little amount is going to be how much water is going to be spilled when you increase the temperature for the glass and also the water. Alrighty, guys, that's it. We're done. I wish you a great day. So I'll see you later. And, well, of course, I'll be receiving your questions on the website and I'll be sending you the problems. Alrighty, guys? So that's it. Have a great day.